Around 150 years ago, the law of conservation of energy was founded, and it just goes that energy is neither created nor destroyed. Later on, you may recognize this guy came along with his theory of relativity. You may recognize it as the first law of thermodynamics. Together, these theories have been banded into the law of conservation of mass, in that the total amount of mass and energy in the universe is constant. Essentially, this means it can't be created, it can't be destroyed, but can only be transferred or converted from one form into another. So how do we go about proving this? We see here a ball sitting at an incline. Its gravitational potential energy is a product of the object's mass, the acceleration due to the Earth's gravity, and the height of the object. This gives us the gravitational potential energy at the top. However, as it rolls down, this gravitational energy is converted into a sum of the ball's translational energy in addition to its rotational energy. This is because, as a spherical object, as it spins, it displaces the distance on the ramp, and therefore it can be summarized as such. This is the formula for translational energy, and we find that there is also a rotational equivalent to linear motion. Instead of m, we have the moment of inertia, and instead of velocity, we have rotational velocity, which is denoted with omega. Looking back at our ball, we can find its velocity through 10 consecutive recorded times taken for the ball to travel down the ramp, and this just ensured a lower possibility for experimental error and uncertainty. The moment of inertia is defined as half the object's mass times its radius squared. We also find that an object's tangential velocity here is equivalent to its translational velocity, therefore equals to its velocity times the ball's radius. The formula for rotational energy can therefore be redefined as such. Using this, we found the rotational energy. The translational energy was also calculated using known values. Going back to the conservation of energy, we find that the final kinetic energy is this. And this isn't the same as the initial gravitational potential energy. However, we calculate the final kinetic energy under the assumption that there is no energy lost due to friction, air resistance, or loss of energy in the form of heat to the surroundings. This is also a possible reason as to why the final kinetic energy is smaller than the initial gravitational potential energy. If we factor this in, it shows that there was indeed conservation of energy. To ensure the validity of this theory, we conducted the experiment again with a differing height. Again, the velocity was calculated, and through this, the final kinetic energy was determined. Comparing this to the initial gravitational potential energy, we find that the final energy is close, albeit slightly greater, and this may have been the result of human error, as the height difference equated to a faster ball and therefore also required a faster reaction time. Proving human error was indeed a contributing factor to the unequal initial and final potential energy, we can rearrange the equation to give us the ideal or theoretical velocity. Putting in height, we yield 2.644 meters per second, and this differs from the subjective velocity, which we determine through our physical timing of the ball's displacement. In conclusion, the very close values of the initial and final gravitational potential of the ball, given the primitive means of ascertaining time of displacement and velocity utilized in the equation to give kinetic energy, is evidence that energy has indeed been conserved. Thanks for watching.